to Quantopticon's virtual booth. My name is Mirella Kolova. I'm the CEO of Quantopticon, and this is Gabi Slavcheva. She's the CSO of Quantopticon. So thank you for joining us today. Before we begin, I suggest that everybody stays on mute for the duration of the presentation. There will be an opportunity for you to ask questions live after this, and you can then unmute yourself and ask your questions, or you can type up your questions in the chat as you think of them, and we'll address them afterwards. So let's begin. I'm just going to share my screen with you. And open up the slideshow. Okay, we just need to admit a few more people. Okay, right, okay. So, right, we are Quantopticon, the only all-female founded, directed and led quantum technology company in the world, and the creators of Quantillion, the world's first state-of-the-art modeling suite for designing and optimizing quantum optical components, systems, and devices. Okay. Right, I think I'm just having a few problems admitting people. Right, okay. Okay, so I'm just going to say a few words about the challenges facing the quantum optics community today. The building blocks of the next generation of quantum technologies are presently actively being developed. However, producing high quality, high performance quantum optical components is a difficult and onerous task due to the lack of adequate modeling tools to guide the design and optimization process. Classical photonics design software can provide initial guidance in this regard, for example, by calculating the optical modes of a given structure, but it cannot provide a fully optimized blueprint owing to the fact that it disregards all quantum phenomena occurring within the device. As a result, a quantum optical component manufacturer is forced to rely on their best guess to come up with a good starting point for the design, whereafter the design prototype must undergo multiple test and modification cycles until it reaches the desired performance. So clearly, this is a very inefficient, long-winded, and costly process. And so Quantopticon solves this problem by creating Quantillion, a unique and pioneering software that can predict the behavior of and then optimize quantum optical components with exquisite precision. Quantillion is based on advanced quantum mechanical theory conceived by respected theoretical physicist Dr. Gabi Slavcheva, and is the product of 15 years of development. Quantillion can address a broad class of problems. It can be used in optical quantum information processing for modeling photon qubits, for example, optical and magneto-optical rotation in a charged quantum dot embedded in a micropillar cavity or in a chiral carbon nanotube. It can be applied to model material or spin qubits, more specifically, all optical control using spin relaxation dynamics in, for example, excitonic states in quantum dots or color defects. With regard to quantum communications, Quantillion can model the emission statistics of single photon sources, such as quantum correlations and time-resolved photoluminescence. And Quantillion can accurately describe coherent propagation effects, such as self-induced transparency and optical soliton propagation, as well as cavity quantum electrodynamics in a charged or neutral quantum dot embedded in a micropillar cavity or an optical waveguide. Furthermore, Quantillion can assist with modeling laser dynamics in pixels, for instance, spontaneous emission and threshold behavior. Our software can even serve as a valuable learning tool for quantum optics students, allowing the student to explore the effect of altering the parameters of their setup. Okay, so the outstanding predictive power of our software is due to a number of exclusive features. Unlike other photonics design software, Quantillion does not describe quantum systems as classical dipoles. Instead, it represents them properly as a set of discrete energy levels. And consequently, an excitation pulse fired at the system redistributes the charge carriers or spin populations among the levels. So Quantillion can actually handle a quantum system with any number of levels, and the quantum system can be an atom, a molecule, or an atom-like system, such as a quantum dot or a color defect in diamond. In addition, Quantillion performs exact calculations and does not it does not make use of any approximations, be it rotating wave, slowly varying envelope, or paraxial approximations. Input pulses and their propagation are modeled using Maxwell's curl equations. The state of the quantum system is represented by the density matrix rho, and its dynamics are calculated using the Liouville von Neumann equation, cast into a form where the dynamics are represented by the real state coherence vector S. We have actually used a Sun-Lee group theoretical method to derive the time evolution equations to generate expressions for the dynamics of the n-level system. So Maxwell's equations are then solved self-consistently with the real state vector form of the Liouville von Neumann equation, also called the pseudospin equation. Quantillion can model open quantum systems, that is where the system interacts with the surrounding environment. More technically speaking, this means that the relaxation and dephasing rates of the system are user configurable and can be selected to reflect the specific interaction with surroundings. The integrated finite difference time domain engine enables the solving of the vector Maxwell's pseudospin equations in the time domain, and hence directly obtains the spatiotemporal dynamics of the light-matter interactions. Furthermore, the user can use a 1D plus time modeling mode if they're working on a rotationally symmetric structure. Otherwise, the 2D plus time mode is also available. Quantillion contains an inbuilt 1D constructor of rotationally symmetric photonic structures, such as DBR stacks, micropillars, nonlinear waveguides, and VCSELs with embedded quantum systems. The user can easily define the exact geometry of the device, which can be made from any material. It's a very general constructor. And in addition, since AlGas is one of the most commonly used semiconductor materials for optoelectronics applications, we have included a refractive index calculator for AlGas alloys. So the calculator can automatically determine the refractive index of the material, given the proportion of aluminium content and the operating wavelength. In addition, the dynamics of a given quantity can be sampled anywhere along the structure by activating a monitor at a specific point of interest. And Quantillion also contains a library of driving pulses and pulse trains with different shapes, as well as random noise. The pulse characteristics, such as amplitude, duration, central wavelength, and polarization, can each be individually set by the user. We can model pulse durations from continuous wave all the way down to femtosecond and few cycle pulses. And this is possible thanks to Quantillion's FDTD engine, which can handle the propagation of ultra-short pulses with bandwidth comparable to the material resonances. Driving pulses can be injected into the device at any point along the structure definable by the user, and can furthermore be deployed at different timings. So I'm going to show you a cartoon of what Quantillion actually does, what it actually models. It essentially sends an optical pulse through a semiconductor structure with or without an active medium, and calculates the propagation of the field and its interaction with the active medium. So I will now hand over to my colleague Gabi Slapcheva, who will demonstrate the software to you and tell you more about the specific cases where Quantillion has successfully been used.
Thank you, Mirella. Well, I'm going to give you a flavor of the graphical user interface that we have developed. Basically, we can map the optical transitions of a particular quantum system, which can be described by discrete energy levels. And we can choose the number of levels. Here is where the number of levels are set. Then we can show the level diagram This is the level diagram for this particular case of degenerate level 1 and 3, and degenerate level 2 and 4. But we can, of course, modify this and, for example, define a generic 4-level system. Which we can define also some energy separation between the levels in this menu, 1.4, let's say, and these are just completely arbitrary numbers to show that the configuration basically is shown. Let me see. The configuration is shown as the levels are shown in this sequence. The energy separations between the levels are set up basically. As you see, level 4 is in between level 1 and 2 in this case. So if we go back to our initial system for which we've got some calculations, I will show you what the dynamics are calculated with this model. This is these are two-level systems which are degenerate and which describe the trion transition in a charged quantum dot. In this particular menu, we can define the allowed optical transitions, dipole allowed optical transitions, and they are shown here. For example, we have allowed here transitions between level 1 and 2 and 3 and 4. On this menu, we set the longitudinal relaxation times, which may be, for example, spontaneous emission times, decay of level 2 to 1, or other longitudinal relaxation times, as I will show later on in the applications examples. Spin relaxation processes, longitudinal spin relaxation processes in quantum dots. The transfer dephasing times are set up from this menu, and the dipole moments of the optical transitions are set up here. Then the structure geometry is constructed, and this is a multi-layer structure with top DBR, bottom DBR, and cavity layer. Here I have prepared the structure working in the strong coupling regime with 25.5 DBR layers, gas layers on the bottom DBR, and 25 gas layers on the top DBR with cavity. In the cavity, we have a quantum dot, indium arsenide quantum dot in the middle of the cavity. The red dots represent points we select in order to sample the time dynamics along the structure. For example, the red dots of the quantum dot represent the left and the right end of the quantum dot layer. And the other red dots are some arbitrary points that we want to monitor the time dynamics. For example, we can select with control mouse some point here and delete it. We can, as you see, the dynamics is, the point at which we want to sample the dynamics is shown here. Then we can calculate the refractive index. Either we can enter an arbitrary, material refractive index. There will be a library of different materials, or we can calculate the refractive index of an all-gas alloy, which is one of the most common materials in optoelectronics. And there is a built-in program which will calculate the refractive index as a function of the wavelength and as a function of the composition of aluminum. We can also define layers with aluminum oxide and define the shrinking percentage of these layers. Basically, we can describe a multi-level structure, a micropure cavity in 1D. Then we can apply pulses, and we can apply not just a single pulse, but a sequence of pulses, which is very important if we want to model, for example, pulse sequence as a spin echo sequence, or other time dynamics upon other pulse sequence excitation. So the pulse sequence, the pulses can have a different shape: Gaussian, continuous wave, of course, hyperbolic second, Gaussian, gain validation pulse. This is a sinusoid which is switched from 0 to 1 within 5 periods, and a random noise, Gaussian random noise. This is the central pulse central wavelength, which can be set up from here. The pulse polarization also can be set up, and it can be, of course, X or Y linearly polarized, or left or right circularly polarized pulse. The pulse duration is set from this menu. Here in this particular case is 100 femtosecond for a Gaussian pulse. But if we define, for example, 2 pulses, we can set the second pulse with different, for example, this is the sesh pulse with 50 femtosecond pulse duration. We can also define the pulse intensity through the pulse area, or we can manually input the pulse intensity here in volt per meters for the electric field. And we can also define delays between the pulses, delays between the sequence of pulses that we want to launch. And this describes much more complicated scenarios. Now the boundary conditions are imposed from this menu separately for the left and right edge of the simulation domain. And these may be absorbing boundary conditions as they are at the moment, perfectly reflecting or perfectly matched layers, or other type of periodic boundary conditions, for example. And here are the results which are visualized and different at the end facet of the structure, which is on the top left panel. On the right facet of the structure, the initial pulse is visualized, or initial pulse sequences is visualized. And then we can choose here from the points that we have set up previously in the cavity, for example, or at the edge of the quantum dot, or at the location of the quantum dot. And for example, we can choose the time. We can choose the time at which we want to calculate the dynamics. It takes some time to load the results, which have been recalculated at the moment, but it can be done also on the fly while the program is running. So we can see immediately what the dynamics are, and what for example, the behavior of the populations of all 4 levels and all field components. In this case, you see that there is at the quantum dot, there is a population flopping, Rabi flopping, which can be even better shown on at later times, for example, this time. And on this menu, on the lower panel, the spatial dynamics is shown just to show that the pulse excites the quantum dot at the location of quantum dot, and the populations are changed due to the passage of the pulse. So this we can also continue from the point where we have interrupted the code on, and this button allows us to continue from the certain point where for some reason we have interrupted the calculation. And we do not need to rerun the calculation, but continue from that point on. Of course, these calculations are quite long in time, and in order to visualize them, they need to be loaded every time, but the behavior can be monitored on the fly. So this is basically what I have to show for the, maybe we'll wait until the final calculation is shown. This is the trace at the final facet, at the output facet of the structure. That is the emission out of the structure. The right-hand panel shows the initial pulse, which is a Gaussian pulse, and it's the 100 femtosecond pulse. This is the time evolution up to this moment, which we have chosen, namely 224 picoseconds. And these are the Rabi flopping of the populations of level 1. Row 1 is with the red in red. Row 2 is the population of level 2. All these populations are of the 4-level system that we are modeling are shown. And on the lower panel, the the spatial dynamics is shown, and we can zoom the position along the structure and see the refractive index profile and the fields profile, and most importantly, where the population is changed. Maybe here, yeah. The population is changed. So this is the one-dimensional code that I showed. Of course, we are aiming to develop further the product and to describe 2 dimensions plus time, or even in 3 dimensions plus time, to model different structure geometries like photonic crystals and other geometries. This is our vision for this software. And now I'll go back to our presentation. Yes, this is not very... Okay, so basically our code permeates all pillars of the quantum technologies, from computation to communications, but it's most relevant for the quantum computation and quantum communication processes. I will give you some flavor of some applications which we've made over the years using this code. For example, we recently showed that in a charged quantum dot, which is embedded in a micropillar cavity, if we launch a circularly polarized ultra-short pulse, this pulse experiences a rotation of the polarization due to the interaction with the spin, which is confined in the quantum dot. The equivalent diagram of the singly charged quantum dot is shown here upon an optical excitation. This is the so-called trion, a singlet transition. And this is basically two-level systems which are coupled through spin relaxation processes. For example, if the electron can be either in spin down or spin up state, and these relaxation processes mean that the spin can flip between these levels, from spin down to spin up, due to hyperfine interaction with the nuclear spins. On the top levels can also experience spin flip processes for the whole, however, in the 3-particle state, which is the trion. This whole spin can flip due to phonon-assisted processes. So we can account for all these dynamics. Gamma is the spontaneous emission rate with which, if we can pump either with left circularly polarized or right circularly polarized pulse, and gamma is the spontaneous emission rate of decay of this trion state. We can also define the dephasing rates of the trion state and of the electron state here through the software. So for this, we've shown first, this is a movie of the dynamics under circularly polarized optical excitation, which is launched from the right-hand side of the structure through an optical fiber. This is the refractive index of the optical fiber. And in the middle of the quantum dot, we have a charged quantum dot. This is a zoom in the vicinity of the quantum dot, showing the population which is excited by the passage of the pulse within the structure. So this is the spatial dynamics. We are interested in the time dynamics at the location of the quantum dot And here on the left-hand side, this is the time dynamics of all of the EX and EY components of the circularly polarized pulse and all populations of all levels. The blue curve is basically the population of the trans states, which we are interested in from experimental point of view, as this is proportional to the time resolved photoluminescence and can be detected in experiment. As you see at the beginning, there is some Rabi flopping, and then it decays exponentially. We can calculate the transmission spectrum of the structure and identify the cavity modes. The cavity mode, this is the active cavity mode when the quantum dot is present. We can compare it with the passive cavity modes when the quantum dot is absent. So in the active case, the quantum dot, if we zoom in the transmission spectrum, we observe this dip in the transmission, which corresponds to the quantum dot transition resonance, and this resonant coherent interaction between the pulse and the quantum dot. We have shown that a giant phase shift can be obtained by using circularly polarized pulse, and this can be of great. This can be quite important for example, for manipulating photon qubits, for creating superposition of photon qubits or high fidelity photon qubit states, because this angle is macroscopic. It's not, as previously shown, quite a microscopic quantity, but the spin photon interactions acts as an entangler and basically leads to this giant phase shift, or which translates into giant polarization rotation angle. Here, excuse me, in this application example, we have modeled single photon sources based on nitrate single photon sources in collaboration with the universities of Cambridge and Oxford. This is the particular structure that we have modeled. It's composed of alternating layers of gallium nitride, doped gallium nitride and porous gallium nitride, with an indium with a gallium nitride quantum dot in the middle of the cavity. And we calculated the cavity emission time trace out of this structure and calculated the correlation functions of the emitted field, the G1 function or the two-time correlation function, as well as the second order coherence. Depending on the noise terms that we insert in the in our Langevin type equations, we can model either classical correlations or quantum correlations, such as anti-bunching, for example. In this particular example, this is very similar to the initial example that I showed. It's a quantum dot which is negatively charged, and there is a confined spin in this quantum dot, but it's in a waveguide. We have shown for this particular example that we can model a single shot readout of a spin state. We can infer the spin state, whether it was spin down or spin up, by launching a pulse across the structure and sampling the time dynamics. We have shown that in the case of a spin up initial spin state, we get this spin echo pulse in addition to the dynamics, which allows us to identify the initial spin state. Also, the blue curve on these curves, on these two graphs, shows the decay of level 2, which is proportional to time resolved photoluminescence, the population decay of level 2. And they have a very different shape. And depending on the shape of this time trace, we can again identify the initial spin state. So it's very important for single shot readout of a spin state for quantum communications using material qubits. We have also modeled control rotation of spin state in a quantum dot in 2 dimensions. Although the code is currently developed in 1 dimension, we are aiming to implement now the 2-dimensional code and to extend our applicability to different, more complex structures. Another application is we have investigated self-induced transparency effects and solitone propagation, optical solitone propagation in waveguides. For example, in this particular example, we have a three-level system in a V-type configuration, and we have shown that a solitone exists in two dimensions, as you see, which is a self-induced transparency solitone. It's not only solitone in spatial domain, but also in the temporal domain. And it excites the population. On the right-hand side, this is the population which is excited by the pulse, which is a 2-pi pulse, solitone pulse. And this population performs Rabi flops in 2 dimensions. Another very interesting example is when we introduce random white noise in this particular case in Maxwell's equations in order to describe spontaneous emission of 2-level systems. So we have a cavity in the micropillar structure, and this cavity is filled with two-level systems, an ensemble of 2-level systems, which are initially inverted into the upper level, and we launch just solely random white noise, introduce random white noise within the cavity. And you see that in the cavity, the field starts to build up within the cavity, and the population exhibits Rabi flops within the cavity. At the output facet, we can see the buildup of the field of sustained oscillations or lasing. Basically, we can determine the lasing threshold in time by this method, solely due to the random noise. And so another example is the pattern formation in microcavities, semiconductor microcavities. In the 2-dimensional case, we have shown that population gratings exist under special conditions with when we pump the structure with an ultra-short pulse. And these population gratings can be used for optical information processing. For chiral carbon nanotubes, if the field is, if the pulse is threading the carbon nanotube axially, we have shown for a giant polarization rotation, which exceeds the polarization rotation induced by even by metamaterials. And finally, we have made some comparison with the experiments at Imperial. For this particular example, we have modeled a p-doped quantum dot, indium arsenide quantum dot, and we modeled the spin manipulation through excited states, upper states, excitonic states in quantum dots, including all spin relaxation dynamics. And we have shown a reasonable agreement between theory and experiment. Well, of course, it will be much improved now when we have developed the model. So basically, these are the examples that I wanted to consider. Now I'm handing over to Mirella.
Yes, thank you very much, Gabby. So I think we're ready to move on to the question and answer session. So please feel free to unmute yourself and ask questions or make comments. We'll be very happy to answer them for you. Oops. Okay, and while we're waiting for...
Is there any in the chat?
Yes, is there anything in the chat? Yes, we have. Okay, that's not a question. Okay, fair enough. So yeah, I would like to actually I would like to add to what Gabby said about the 1D and 2D model. So the 1D model is completely fully implemented into the software. The 2D model is not complete, but we can, if you desire a 2D solution, we can do this for you on a consultancy basis. So we can calculate this for you. We just have to do it in-house. Yeah, and I would also like to announce that we will upload a demo version of Quantillion on our website by the end of the day, so that it should be available for you to download and try it out and play with it by the end of the showcase event. So we have a comment from Mark Day. Thank you very much. Okay, the question is, can you let us know which groups or companies have used our software, please? Gabby, would you like to take that question?
Well, up to now, we have shown these capabilities to OptiWave, and they were really impressed with our capabilities and are interested in collaboration. OptiWave is a Canadian company for photon design. We haven't calculated for particular companies.
We haven't worked with industry so much, but we have worked with
academia,
with Professor Rachel Oliver's group in the Department of Materials in Cambridge University, and also with Professor Robert Taylor's group in the condensed matter physics department in the Clarendon Laboratory at the University of Oxford. We're also preparing to launch a collaboration with Professor Kai Müller at Technical University Munich. He's in the Walter Schottky Institute at the university in particular. Yeah, this is it for now. Yep. Yeah, so feel free to ask more questions. We still have a few more minutes left. We have about 8 minutes before our session is over. Thank you. Yeah, in the meantime, you can feel free to follow us on Twitter and LinkedIn. These are our details here. But yeah, if you just type Quantillion into one of those social media platforms, you can very easily find us. Yeah, and yeah, this is our website where you can download the demo and for free, and you can play with it as much as you like, see how it works. Yeah, so we'll just we'll be here for a few more minutes in case you want to ask any more questions.